Hi to everyone and welcome to this Epoxy Technology webinar. My name is Rich and I'm a Senior Manager with IEEE GlobalSpec, and I'd like to review just a few housekeeping items with you before we get started. I'd like to take a moment to help familiarize everyone with the operation of the user interface for today's webinar. Now, the large window that you're currently viewing with the heading presentation in the upper left, that's going to be the primary window for the webinar. If you look to the right of the main presentation window, you should see the speaker's bio window, and that contains background information on today's presenter. Now, just below that, you'll see a Q&A window, and at any time during this presentation, you can enter a question into the box in the lower section of that window and then click Submit. Your question will then be placed in the queue for our speaker to address when we get to that Q&A session. Now, if you look to the bottom of your screen, you should see additional buttons that will help enhance your webinar experience. If you'd like to see what a particular button does, just hover your mouse pointer over it, and a tooltip will appear with a description of that button's function. Okay, right now I'd like to introduce today's presenter. Brian Bruce is the Manager of Applications Engineering Lab at Epoxy Technology Incorporated. Brian has over 8 years of specialized training and experience in epoxy and UV adhesive applications. He has supported numerous Fortune 500 companies in their manufacturing assembly and bonding needs. As a trained adhesive solution provider, Brian has assisted customers through personal visits, presentations, training seminars, as well as through targeted technical application-specific correspondence. Brian holds a bachelor's degree in chemistry from Wheaton College and received an undergraduate award in analytical chemistry for his outstanding work. So Brian, welcome to today's event, and with that, I'm going to pass things over to you to get us started. So Brian, go right ahead.
Hello, my name is Brian Bruce from Epoxy Technology, and today I'm going to be presenting Epoxy Technology's advances in thermal management. In today's presentation, we will be covering thermal conductivity and its mechanism, the impact of cure on thermal conductivity, thermal resistance versus thermal resistivity, resistance in device, and our brand new triple layer thermal conductivity measurement technique. In today's presentation, I'd like to take you on a brief journey of Epoxy Technology's understanding of thermal conductivity. First, what is thermal conductivity? Thermal conductivity is the diffusion of heat from an area of high heat to cool. That energy transfer occurs through molecular collisions, and it can be quantified through Fournier's law, which you can see below. Epoxy Technology has continued to push forward our knowledge and understanding of thermal conductivity because of customer demand. As microelectronics continue to shrink, higher and higher heats are generated on a smaller and smaller footprint. That necessitates high thermal conductivities to keep devices cool and efficient. LEDs are one such example, where high heats and high powers can lead to degradation and reduced lifetime of LEDs. Looking into high thermal conductivity, Epoxy Technology has tested many different materials or raw material fillers to help augment our epoxies. One of the most common, though, is silver. You can see on the thermal conductivity chart that silver is one of the highest thermal conductivity materials that can be added to an epoxy system to generate those high thermal conductivities. Now, you can also see in this chart that silver's bulk thermal conductivity, that's the thermal conductivity of a block of just pure silver, is extremely high, in the near 429 watts per meter Kelvin range. This is significantly higher than, for example, when it's put into an epoxy resin system, where we've tried to achieve typical thermal conductivities of 2.5, and we're pushing the boundaries going up towards 60 watts per meter Kelvin. But once the silver is suspended in epoxy resin, the thermal conductivity is typically far lower than the bulk silver thermal conductivity. In investigating thermal conductivity, we first noticed that thermal conductivity and electrical conductivity are extremely tightly correlated. And that is based on the fact that electrical conductivity and thermal conductivity both require a good path for the electrons or heat to be dissipated. In the case of a silver conductive adhesive, that means a direct contact between silver flakes. The better the overlap, the better the conductivity. Enough filler needs to be loaded into the system to overcome its percolation threshold. That's the minimum amount of filler that's required to get good interparticle contact. And that will vary, that percolation threshold will vary with different materials and fillers that we add into our epoxy solutions. Overall, the exact mechanism of electrical conductivity is still debated, but what is generally considered the standard mechanism is particle-to-particle contact. That would be the silver flakes pulling into a tight cross-link or a tight pattern in which they can easily pass electrical signals. Epoxy technology has looked at ways of optimizing that overall connection or overlap by optimizing our shrinkage, the exact materials in terms of the silver that's packages that are put into the material. And through all these optimizations, we have found that not only are the proper resin and hardener systems required, but the optimal cure is required. Cure has a dramatic impact on electrical and thermal conductivity. In our testing, we've looked at several materials that we've optimized for high thermal conductivity over cure. You can see here 3 of our popular high thermal conductivity materials with their thermal conductivity over cure schedule. Some, like the H20E, are minimally influenced by the cure itself. Others, like our EK1000, are affected dramatically by a cure, where here you can see with a lower temperature 150 Celsius cure, you achieved a 12.6 watts per meter K thermal conductivity. With a higher temperature cure, you actually negatively influenced that thermal conductivity, resulting in about an 8.8 watts per meter K thermal conductivity. And finally, with a stepped cure of 150 Celsius for 1 hour plus 200 Celsius for 1 hour, we were able to boost our thermal conductivity to 26.3 watts per meter Kelvin. So our previous slide focused on the thermal conductivity, or its inverse, thermal resistivity, which is a bulk property of the adhesive and is device independent. We have pushed the thermal resistivity of our products as much as we could, but as we continued to interact with customers and have things tested in device, we realized that truly thermal resistance, the ability of the material to actually dissipate heat in device, was the critical property, and that thermal resistivity or thermal conductivity and thermal resistance were not necessarily correlated. One of the first things we noticed was that thermal resistivity does not vary with sample thickness. This will become critical as we continue to examine and determine the difference between a bulk thermal resistivity and an in-device thermal resistance. Thermal resistance, on the other hand, is influenced by bond line thickness. Thermal resistance is the ratio of the difference in temperature differential to power dissipated. That means it's only valid for a specific distance or bond line thickness, a specific power load, and a specific temperature range. On the right, you can see thermal resistance versus bond line thickness. As the bond line increases along the x-axis, so does the resistance. Here you can see an example LED where we've broken down to show how many resistance layers you will have to go through to actually wick heat away from the heat generating semiconductor LED down into the heat sink. The bulk adhesive resistance is absolutely critical. But just as critical is its ability to interface with the LED and with the substrate and to optimally transfer heat away from the heat source. When we've actually tested in part or had customers assist us testing thermal resistance in part, we found that just because somebody claims a high thermal conductivity on a data sheet does not necessarily mean they have a high thermal resistance in part. Our testing with IR cameras on both large and small die showed that high thermal conductivity as a data sheet property can absolutely be outperformed by something that has an overall better interface with your part. We found this a little interesting, a little unexpected overall, assuming that bulk thermal conductivity would really be the way to go. So to figure out what was happening, we knew we needed to investigate further. We started to look at SEMs, cross sections, to try to investigate what might be happening at those interfaces. Over the next couple of slides, we'll be looking into examples of both ideal bond lines and common bond line issues, with some corresponding actual part SEMs. We're looking to illustrate the importance of both bulk and interface within a bond line, and why actual customer parts are not always an ideal case. That in an ideal case, you have the silver very well wet to the semiconductor, no voiding within that region, good solid connection of the silver flakes directly to the semiconductor, a solid pathway for that heat to transfer down into the substrate, filler uniformly distributed through the bond line, good strong adhesion between the substrate and the semiconductor overall, and no large CTE mismatches that would cause delaminations to occur. In these ideal cases, the interface resistance is very, very low. You can see on the right side an example of what we would consider a fairly ideal bond line. Epoxy Technology's H20E, its thermal conductivity and its thermal resistance in part are very commonly the same because it makes near ideal bond lines and wets very well to the substrate and creates minimal resistance at the interface. Not all bond lines are an ideal case, though, and resistance may vary significantly, even within using the same adhesive, because of small interface issues like delamination. Many highly filled adhesives have poor adhesion because they just don't have a lot of adhesive in them. They are very highly loaded with silver. Another trick that's used to boost thermal conductivity is loading the material with solvent. Those solvents can become trapped within a bond line and during cure can cause shrinkage and delamination, pockets where those solvents were stuck or couldn't be removed from the bond line. Stresses such as CTE mismatches can occur, and those can also cause delamination within the bond line. Overall, what's happening here is the creation of an air gap, and air is one of the best insulators there is. Because you have two interface layers with bad thermal conductivity, the overall bulk thermal conductivity of the adhesive is not able to overcome that inefficiency. And because of that, you can actually have very bad thermal resistance from a very high thermal conductivity product. Another common issue is filler settling within the bond line. Many of these high thermal conductivity silver systems are very highly filled with silver, and they use low viscosity resins and solvents to push up or optimize their thermal conductivity. Because of the high density difference between the silver flake and the resin itself, that resin can start to settle. You can have large groupings of that silver at the bottom of your bond line and a resin-rich layer at the top. That resin is not very thermally conductive. It's quite insulating overall with a thermal conductivity of only about 0.35. Again, your resin-rich layer, similar to the air layer in your delamination, is adding a large resistance at the interface and is going to be a far bigger contributor to your overall thermal conductivity than a high thermal conductivity of the bulk material. It's not going to be able to make up for the difference. Very similar to delamination, we also see air voiding. This is a product that is very high in viscosity because it has so much silver. As you add silver, as you load the material more, the viscosity tends to go up, up, up. To do that, to then apply it to a substrate and dye, you can have little voids, little air gaps that don't get filled in with the material. Again, air is a terrible thermal conductor, one of the best insulators there is. So again, you're going to have a large resistance at the interface that the bulk epoxy just can't make up for. As we've mentioned, many of these silver high thermal conductivity systems use low viscosity resins or some type of solvent. Now, if you end up using a lot of solvent, that solvent can get trapped within the bond line. You can actually seal that in, which creates this kind of gummy, uncured layer because the solvent ends up sitting within the system and plasticizing the bond line. The filler particles are not fully pulled together like in an ideal case. And in this case, it's not the interface that's being affected, but the bulk thermal conductivity of a closed bond line, which is being affected. As we've gotten further and further into our understanding of thermal conductivity, we've realized that the in-device thermal resistance is what really matters to customers. But that thermal conductivity is what is tested in the industry. Most customers assume that a high thermal conductivity on the datasheet is going to mean good low resistance in their part. But as we've shown, that requires an ideal bond line, and that's not always the case. The current industry standard for measuring thermal conductivity is laser flash testing, done to ASTM E1461. You can see an example of a typical sample on the right side. Those samples are sanded, cured in an ideal way, and are much thicker than a typical epoxy bond line. Overall, this is idealized for the sample system or the epoxy system being tested and is very much focused on the bulk material result, does not take into effect the interface within an application. Epoxy Technology trying to find a better way to simulate our customers' parts has created a 3-layer thermal resistance in-device simulation. This is very similar to the standard laser flash method, but instead of using a large disc, sandwiches the silver epoxy between 2 copper discs. Those copper discs will allow the epoxy to have an interface layer, or in this case, 2 interface layers, and the bulk epoxy that will all be contributing factors to the thermal conductivity that is measured in the laser flash system. This type of simulation better shows settling, voiding, wetting, delamination, and the sample thickness is very similar to what you actually see in a bond line. In fact, 5 mils is a little larger than some bond lines, smaller than others, but nowhere near the 12 mil that is of a typical sample. Once this method was developed, we looked at the bulk thermal conductivity versus the triple layer thermal conductivity laser flash testing, and we found a very interesting correlation. Finally, we were able to find some of the materials that our customers had said in part were extremely high thermal conductivity and correlate them directly to a thermal conductivity measurement. Here you can see the bulk thermal conductivity of H20E had a very similar triple layer test, which confirmed that it was creating very ideal bond lines. Our EK1000 would routinely show thermal resistance in device that was extremely, extremely good. This shows you that the overall interface effects are minimal with something like the EK1000. That is one of our high thermal conductivity materials. Now, we made a longer dry out version of that EK1000 called the EK1000-1. That product actually shows a great bulk thermal conductivity, but just the littlest bit of a dip in the thermal conductivity in the triple layer testing. That longer dry out absolutely has affected the interface and the bulk material. We suspect that some of that solvent may have been trapped within the system. To further investigate what was happening, we took these cross sections. These are the bulk samples versus the triple layer samples. We took those and cross-sectioned them with SEM. You can see in the bulk sample and the triple layer sample for our H20E a very uniform silver distribution. In both cases, you can see no evidence of voiding, delamination, resin-rich layers. There is just a uniform high silver content throughout. No air, no resin-rich layers, giving you a good heat dissipation. One of the R&D materials we had tested in a similar way, we did the bulk sample and the triple layer sample. In the bulk sample, you saw an excellent high density silver, uniform flake distribution, a very high overall thermal conductivity in the bulk sample. When we then received back the triple layer sample, looking at the bond line, we noticed that trapped solvent that I had mentioned before, that in sawing the sample open, we actually were pulling out plasticized resin. And that illustrates that the silver flakes were not being pulled together optimally, and you weren't actually getting optimal thermal resistance within the bond line. Looking at our EK1000, this, again, we saw very similar results between the bulk sample and the triple layer sample. The bulk sample showed excellent, very dense silver flake throughout, uniformly distributed in the sample. The triple layer sample showed a very similar effect. Along the edges, there were no large air gaps, no delaminations, no high resin-rich layers, and a nice smooth cut, meaning that there wasn't residual uncured material in the bond line that would affect its bulk thermal conductivity. Here, not surprisingly, thermal resistance in device reflected the bulk thermal conductivity. So, because of this kind of information, we received questions from customers. Can a material with incredibly high bulk thermal conductivity properties ever outperform something that has a better interface resistance? There are reports of new products on the market, sinterable silver systems that have thermal conductivities in the 140 watts per meter K. Could something with as low as a thermal conductivity as 26 watts per meter K ever compete? Well, in several of our in-part customer tests, the EK1000 outperformed the silver sintering system, and we wanted to investigate why. So we put the claims to the test. We tested this 140 watt per meter K thermal conductivity silver sintering system. And overall, we saw that in the bulk thermal conductivity, it showed excellent results, truly exceptional. Nearly 70 watts per meter K in our testing. Excellent. But once we put it into our triple layer thermal conductivity, that thermal conductivity dropped to 4.7 to 7.5 watts per meter K. The EK1000 performed 3 times better in the thermal resistance testing, in the triple layer testing. We again cross-sectioned this product, putting it through SEM, and on the left side you can see the bulk sample looks beautiful. Actually does sinter. You see a uniform cohesive bond line. The filler does appear to be coming together, but you can also see that in the bulk material, there's a very high polish to it. It was clearly sanded and manipulated. All the solvent within the system was allowed to come out. On the right side in the triple layer, you can see large gaps and areas where the material delaminated, where there was solvent trapped within it. And because of those binder agents that remained, the triple layer sample just was not the same. The 140 watt per meter K bond line in cross-sectioning had several different areas, ideal areas, delamination areas, and trapped solvent areas. This wide variety of conditions within the bond line shows that it unfortunately cannot make an ideal interface. The spheres you see within the bond line are glass spacer beads to try to create a uniform bond line. And in the delamination areas, you can see those silver beads are have nearly shrunk away, and the silver has shrunk so much that it's pulled away from those spacer beads and pulled away from the substrates. A similar thing with the trapped solvent. How much of that was dug out in the cross-sectioning process because it wasn't fully polymerized and wasn't fully linked together. Those inconsistencies create large issues in terms of air gaps, delaminations, which gives you very poor thermal resistance in part and in this triple layer test. Additionally, many of these high thermal conductivity materials use low molecular weight resins, diluents, or even solvents to achieve their high thermal conductivity. Dry out is absolutely a concern. And with some of the high thermal conductivity materials on the market, I've heard customers complain that they only have 15 minutes of processing time from the time the dot is placed to the time it has to be the die attached and put into an oven. With If it exceeds that 15 minutes, the dye doesn't actually wet into the silver fill system. You don't get a nice fillet and you don't get a good interface. The material becomes too hard and too high viscosity to the point where you actually get that trapped air and non-wetting effect that we discussed. The EK1000 was designed for a good dry out time of about 1 hour in dot form and 1 day in the jar. We had customers say that wasn't quite long enough for their processing, so we created the EK1000-1, a longer dry out version. That has a 7-day dry time in jar and a 1-day dry time in dot. As we've discussed, air is one of the best insulators there is. And that can affect syringe packaging as well. How you get and use the material can have a huge effect. Customers that were creating their own syringes, sometimes that would have bubbles or voids. Those syringes would not give them the thermal conductivity of syringes made by Epoxy Technology. Our packaging has been optimized to give you high thermal conductivity, minimum voiding or bubbling through the material. That electrical and thermal conductivity is a direct correlation to your ability to actually properly package the material. On to the conclusions. First, cure matters. Stepped cures and high cure temperatures typically increase thermal conductivity. That an optimal cure will help optimize your thermal conductivity. Interface matters. That a high bulk thermal conductivity is not a great predictor of the actual thermal resistance in device. That we suggest a triple layer laser flash test to give further insight into how the product will actually perform in your device. And that processing matters. The syringe packaging process absolutely plays a critical role in terms of the thermal conductivity you can get. Epoxy Technology offers all of these products that we've discussed today in pre-mixed and frozen single component syringes. If this would be something you would be interested in, please contact us. And finally, the EPO-TEK EK1000 family of products continues to outperform many products with higher bulk thermal conductivity claims because of its in-device performance. Its ability to minimize the resistance at the interface layer creates optimal conditions for thermal management. Thank you very much for your time and attention today. Again, this is Brian Bruce for Epoxy Technology. I will now be taking any questions you guys have. So let's see what you got.
Brian, thanks so much for that great presentation. Now we have some questions that have come in from our attendees, but before we get to those, let's remind everyone if we don't get to your question, don't worry. We'll have an answer for you following the webinar. The complete Q&A transcript, including answers we don't have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into that on-demand mode. Okay, Brian, so you have the questions that have come in from the attendees right there, so why don't you go right ahead?
Let's see here. Questions coming in. The first one, does stepped curing indicate expected results for thermal management at the part design level? Well, stepped curing can produce a massive improvement in terms of thermal management. Thermal conductivity can increase significantly with a good stepped cure. For example, the EK1000 material that we offer, we've seen a massive increase going from a 150C cure, which gives you about a 12 watts per meter K thermal conductivity, to a 150C plus 200C cure. You can get near 26 watts per meter K thermal conductivity. And we've in fact had customers test the material with a multiple 3-step cure, and they were able to boost the material's thermal conductivity up to about 36 watts per meter K. So designing that into your process, into your process flow, will give you a massive benefit in terms of the actual thermal management within part. That just needs to be taken into consideration in terms of how you're expected to do your cure schedule, because stepped cures will take a longer amount of time, but it will give you a better result overall. Let's see. How can I match thermal resistance testing versus the thermal conductivity data on the data sheet? Oh, that's a great question. Something that I was hoping someone would ask, because the presentation here really goes into the kind of abstract concept of how thermal resistance at the bond line is affected by both bulk conductivity and interface conductivity, but how does that actually affect your parts and your testing? Well, overall, this testing can be done in a customer's part. The customer's part is usually looked at with something like an IR camera to see how heat is actually flowing through the device. People less commonly are actually testing the bulk epoxy material and are testing more in part. Laser flash is excellent for looking at the bulk conductivity, and in fact with the triple layer test looking at the interface resistance as well, but actual in-part testing done with an IR camera will give you the most accurate overall picture of thermal management in your particular device. Why is resistance at the interface different than bulk resistance? Well, this question really gets to the crux of this presentation in terms of why they're different. Well, the interface and the bulk material are two important contributing factors. They're just different pieces of the whole puzzle, both needed to understand the resistance in part. We sum this up really especially with the bulk laser flash sample versus the triple layer sample. The bulk samples remove a lot of the contributing factors like delamination, filler settling, or pore wetting, and really focus only on the bulk resistance, versus the triple layer samples. Those add in a lot of those interface factors and look much more at the holistic thermal management of your part. Can all adhesives improve thermal management with a stepped cure? Well, some can and some don't. Some can definitely be improved. Our EK1000 is such an example where a stepped cure creates a massive improvement in thermal conductivity and is strongly recommended if you can. Our H20E, on the other hand, that material actually doesn't see a significant increase in its thermal conductivity with a 150C cure versus a 150C plus 200C stepped cure. The difference there is definitely the amount of reactivity. The H20E is already completely reacted at that point, whereas the EK1000, those silver flakes are continuing to pull into tighter, more organized contact, which is really what's creating an ideal case for a thermal conductivity. So overall, it really depends on the adhesive system. For EPO-TEK materials, you can certainly contact us if you have some specific questions on products, because this is definitely something we've continued to look into, and would be happy to give you ideal cure schedules that we'd recommend. Another here. How does silver flake distribution affect thermal conductivity? Well, thermal conductivity is strongly affected by silver flake distribution. You could see a lot of the SEMs that we showed today that in the ideal case, the silver distribution was very uniform. That uniformity of silver flake means that there is a consistent signal going through the material. There's a lot of overlap in the silver flakes, so heat is able to be quickly drawn out of your semiconductor. If you have a disproportionate, non-homogeneous silver fill, you actually end up close to the filler settling example that we discussed earlier, where you're going to have a resin-rich layer or an area where there will be a much higher distribution of resin and less overall silver. That resin is not anywhere as thermally conductive as the overall silver package put into the material, and it's going to dramatically lower your overall thermal resistance in part.
Okay, and with that last question, we're going to wrap things up right there. Brian, thanks so much for taking some time to be here with all of us today. And we'd certainly like to say a special thank you to all of our audience members for being part of this webinar event. Now, we'd like to let you know that you will be receiving an email from us with a link to the on-demand version of this presentation, a PDF of this PowerPoint, an FAQ document, along with a Q&A transcript. So lastly, please just take a moment to complete a survey, which will appear on your screen at the end of this live webinar. For those folks who may be viewing this on demand, you'll find the survey located along the bottom of your attendee console in the survey widget. So again, thanks for taking the time to attend this webinar event. Take care and have yourselves a great day.